So last class we talked about logical positivism, summarized the different commitments of the positivist, and various reasons why the positivist paradigm kind of fell apart. We ended with 5 different problems. One was the problem of self-refutation, that by its own standard, positivism is false or meaningless. We talked about what I labeled the centurion problem. We talked about holism, the idea that you can't test sentences in isolation. So sentences or hypotheses can only be tested in conjunction with other assumptions that you take for granted, which could potentially be revised. We talked about Quine's argument against the analytic-synthetic distinction. And one other thing we talked about that I listened to the lecture and thought I should have been more precise here. Positivism, I said that positivism does not make sense of actual scientific practice, because unlike what the positivists said, scientists do often postulate unobservable entities. And that's right, but that's just a descriptive point. Descriptive meaning, describing how science works. But I should have added the normative point that not only is it true that scientists in fact do this, but it's been useful to do so, right? It's been very fruitful to postulate unobservable entities and try and derive predictions from them, which counts against doing it the positivist way. And even though, as I say, positivism is now almost universally rejected, there are some good takeaways. It can be a good reality check, right? It's a good way to keep you in touch with observation. Additionally, I do think the criticisms that they made of the views that came before were often good. Often the most important contribution of a movement is the criticism of what came before, not necessarily their positive contributions. Often what the movement puts forward has its own problems, but the criticisms they make are often valuable. I do think they were right that Hegel and Heidegger, people like that, were writing a bunch of nonsense. So today, obviously, we're talking about the philosopher Karl Popper. And so I want to start off with a few comments about him. So if you ask ChatGPT who is the most important philosopher of science who has ever lived, at first it will resist and say, oh, that's kind of hard to judge. But if you force it to answer, eventually it will say Karl Popper. And that's not just the view of ChatGPT. Many historians of philosophy of science will say that he's the most influential philosopher of science who has ever lived. And unlike many philosophers of science, he is actually widely respected by scientists. Scientists often hate philosophers, and sometimes the hatred is justified. But if a scientist respects one science, if you hear a scientist say, I respect one philosopher, odds are it's going to be Popper. As one scientist put it, there is no more to science than its method, and there is no more to its method than what Popper has said. So a pretty bold statement. I don't think I would go quite that far, but that is how a lot of scientists think. A lot of them have a lot of respect for Popper. And not to get too personal, but I have a bit of you could say, a history with Karl Popper. I first read his book Conjectures and Refutations in 2018, and it had a huge impact on me in many ways, as I'll be saying later. But before we actually get to before I say that, I'm going to show a video from Paul Meehl. Paul Meehl had a similar story to mine. Paul Meehl read Popper's work and became a full-blown Popperian, a full-blown Karl Popper person. But after reading various criticisms, he decided that he was a neo-semi-demi Popperian, I think is his term. So maybe just Popperian in spirit. So I'll show that clip and then say a little bit more. So what is Popper's basic view? You can summarize it pretty simply. His basic view is that science always starts with a guess or a conjecture, something you make up, and then you attempt to falsify it You subject the guess to experimental tests that are aimed at refuting the guess. If the conjecture does not survive the attempted falsification, if its predictions do not come out, then you throw the guess away. The guess has been falsified. If the guess does survive your attempt to prove it wrong, that doesn't mean it's more likely or proven, it just means it has survived the attempted falsification for now. And with that, we could go home. That is basically the core of the idea, but obviously there's more to say than that. So to help you see why this was such an important insight, we first have to talk about the content in chapter 3, which is on something that motivated Popper's view of how science works, which is the problem of induction and various related issues. So to understand the problem of induction, we have to contrast induction with deduction. So these are two methods for proving or supporting ideas. So deduction and induction. So I don't think I used the term last class, but some of the examples I gave last class would be examples of deduction. So the Socrates example. So premise 1, all men are mortal. Premise 2, Socrates is a man. Conclusion, Socrates is mortal. So let's look at this example. So the defining feature of deduction is that the premises, if true, guarantee the truth of the conclusion. Right? If premise 1 is true and premise 2 is true, the conclusion has to be true. Induction, by contrast, in the standard view, can only lend probabilistic support to the conclusion. If the premises are true, they increase the probability that the conclusion is true, but they don't prove it to be true. Another feature of induction is that it involves moving from particulars to a generalization. So the direction is like this. Particulars to a generalization. So for example, I get a sample of swans, look at what color they are. If the swans in my sample, each of them is white, I conclude all swans are white. I move from a set of particular examples of swans to a general statement, namely, all swans are white. Deduction often moves in the opposite direction from generalization to particular, but it doesn't have to. So in this particular case of deduction here, you start with a general statement, all men are mortal, and you move to a particular statement, Socrates is mortal. So, but induction always goes in this direction. That's a defining feature of induction. I see some puzzle books. Does this make sense so far? Any questions about the differences I've talked about? Okay. So here's the task I have in chapter 3. I have to explain why many philosophers have argued that this second process has no rational basis. This goes back to people like David Hume. He's probably the most famous proponent of this. People like Hume and people who came after him have argued that there is no logical or rational basis for moving from particulars to a generalization. There is no rational basis for inference that is probabilistic in nature. This is a very radical claim. You don't necessarily have to buy it at the end, but you should at least be able to understand why people like Hume argued this. We will see that there were many attempts after Hume to create an inductive logic, and these were, on the whole, a profound failure. So let's start with Hume. Let's look at how he argued this. So remember from last time that Hume thought there were two ways of knowing things. Can anyone tell me what those two ways are, according to Hume? The two categories of knowledge. So the two are relations of ideas or as the positivists call them, analytic truths, and matters of fact, or as the positivists call them, synthetic truths. You'll also see a priori and a posteriori. And the distinction is relations of ideas you can know to be true as a matter of definition. So deduction would fall under the umbrella of relations of ideas, so would mathematics. So 2 + 2 = 4. You don't have to go into the world and do experiments to find out that 2 + 2 = 4. It's just true by definition. Or all bachelors are unmarried. Matters of fact you can only find out, according to Hume, via observation. You have to go look at the world. So, if we go with Hume's idea, these are the only two ways to know, let's look at induction. Suppose someone says, well, I'm skeptical of induction. How could you prove to them with one of these two, that induction is a sound way to reason? And I'll focus on just a specific example that's often used. So here's a case of inductive inference. The sun has risen every day that I've observed in the past. This is a shorthand for a set of particulars, right? So it rose all these days that I've observed, and conclusion, the sun will rise tomorrow. So this is an example of probabilistic or inductive inference. So someone who's a skeptic comes along and says, how do you know that the conclusion follows from this in any sense? And Hume says it has to be one of these two. So let's start with the first one. Does this follow from this as a matter of definition or logic? And when we're dealing with inference of the top kind, where it's just a relation of ideas, it has to follow as a matter of definition, which means it's not possible, it's not imaginable that the premise or the premises be true and the conclusion be false. So, like, take the Socrates example, right? So, all bachelors all men are mortal. Socrates is a man, therefore Socrates is mortal. You can't imagine a situation in which the two premises are true and the conclusion is false. But in this case, obviously you can. You could imagine it being the case that the sun rises every day in the past, but does not rise tomorrow. Maybe the scientists are wrong and the sun blows up, while we're asleep. And you may say that's kind of a crazy example, but the point is, in order for it to count as this kind of proof, it's very strict. It has to follow purely as a matter of definition. Okay, so what about the second kind? Can we say that inductive inference is justified on the basis of observation? And Hume is going to say no. But let's see how we might justify it. So here's the present. And this is the past, this is the future. you could say that when we used inductive inference in the past, it worked. So we saw the sun rise several times in the past, and back then we assumed it will rise in the future, and it came true. So we've seen in the past that inductive inference has worked. When we use the past as a basis to draw inferences, it's worked. Therefore, it will work in the future. What Hume says is that that argument is an example of begging the question. Does anyone know the meaning of this? This is a fallacy. Any of you take a critical thinking or philosophy class? What's the meaning of begging the question? So, begging the question is making an argument where you assume the conclusion in order to prove it, thereby making it a not very convincing argument. So, just a classic example. Suppose you're arguing with someone about religion, and someone's trying to defend the divine inspiration of the Bible. Now, I'm not saying you can't make an argument for that, but this would be an example of a not good argument. So you ask someone, why do you believe the Bible is divinely inspired or true? And they say, well, it says in 2 Peter in the Bible that the whole Bible is true. It's like, well, that's only a good argument if you already assume that the Bible is true and what it says in 2 Peter is true. So it's not a very convincing argument because you're assuming the conclusion in order to prove it. So this would be a case of doing that. The conclusion that you're trying to prove is inductive inference. In this case, you're trying to prove that the future will resemble the past, which is part of inductive inference, or an example of inductive inference. And in order to prove it, you're saying, look, well, induction worked in the past, therefore it will work in the future. But that's only a convincing argument if you already assume that the future will resemble the past. You're saying, well, induction worked in the past, therefore it will work in the future. Now, this may seem like kind of a strange thing to say, but if you believe that begging the question is a fallacy, that rules out using this second kind of argument to support induction. So that's Hume's argument in a nutshell. There's only two ways to know things: relations of ideas and matters of fact. The top one you use just definition, just what follows by definition, and the bottom one you use observation. And Hume's argument is the first one doesn't work because this does not deductively entail this. It does not entail this as a matter of definition. And if you try to use observation to prove induction, you wind up begging the question. This is I suspect, a counterintuitive idea, but does that make sense? Does anyone have any questions about Hume's argument? So Hume's solution to this was to say, well, that's too bad, we have to use induction. So he says that we use it just as a matter of animal instinct or habit. It's not something we can prove rationally, but oh well, we have to use it. So it's just something that we do, as I say, as a matter of habit. But people like the positivists and various philosophers of science after were not pleased with this, so there were various attempts to create inductive logic. And I won't go through everything in this chapter, every attempt, but I'll go through some highlights, just to give you a sense of the difficulties that these attempts at creating an inductive logic ran into. The first attempt we could put under the heading of hypothetico-deductivism. So hypothetico-deductivism works something like this. You have a hypothesis, a guess, and you deduce a prediction from it, and then test it. I mean, Popper technically will be a type of hypothetical deductivism too, but what they tried to do was this. They said what you can do is say, premise 1, if H, then O. So if the hypothesis is true, and it could be a generalization of some kind, all swans are white, then we should observe X, whatever the prediction is. So you can't look at every swan in the world all at once, so you may say, if all swans are white, when I go to this lake in France and look at swans, I should see white swans. That's what I should observe. And 2, that's what I observe. And let's say I do observe what follows from that conclusion, therefore H. So notice right off the bat, this is not deductively valid. I gave a teaser for this last time. The fact that it's true that if H, then O, and O, that does not entail H. Here's a silly example that my prof used to use. So I'm going to give an example of these two, where both the premises are true. And if both the premises are true, it should guarantee that the conclusion is true. Let's say my hypothesis is that I am the strongest man in the world. So if I am the strongest man in the world, I should be able to lift a felt. Surely that's true, right? If I'm the strongest man in the world, I can definitely lift a felt, right? That follows. So premise 1, if I'm the strongest man in the world, I should be able to lift a felt. Premise 2, conclusion I am, so obviously that doesn't follow. The fact that a hypothesis entails something, and you find that thing, doesn't prove that the hypothesis is true. Now what you could do, if you wanted to be sneaky, you could say, if I observe this, then the hypothesis is true. I observe that, therefore the hypothesis is true. That does follow. That is logically sound. So if I see this, then the hypothesis is true. I observe this, therefore the hypothesis is true. This is called modus ponens. The trouble is, for any interesting hypothesis, one will never be true. It's never going to be the case that one observation entails logically that the hypothesis is true. So sometimes I may be thinking, why don't we do that? That's why. Premise 1 is never true for any interesting hypothesis. So, okay, well, is there anything we can do here? What various people tried to do is say, well, maybe it doesn't follow deductively that this is the case, but maybe it just makes it more likely. If this is true, then this should be true. We saw that. Maybe the conclusion is this is more likely. Is there a way to cash that out? So there are two problems with that. One I'll just mention in passing because the book mentions it. If this works, if it works to say if H then O, O therefore H, even if you're just saying, H is more likely, technically, it is equally valid to say if H, and anything you want, X. And for X, you can put in any statement, then O. Therefore, H and X. So let's say our hypothesis again is all swans are white. Then I should observe white swans in this lake in France. I could just as easily say, if all swans are white and the moon is made of cheese, then the swans in the lake in France should be white. I see white swans in the lake in France, therefore the statement that all swans are white and the moon is made of cheese is more likely. Don't worry about that one, I won't test you on that one. Just trust me, it is the case that if you assume that this kind of argument increases the probability of H, it's equally logically true that it increases the probability of H and anything you added onto it in premise 1. Another problem with using hypothetico-deductivism in this way, or I guess I shouldn't have raised that. Any questions about the points I've made about hypothetico-deductivism? Another consequence of assuming it's the case that confirmed predictions increase the probability of the theory is the Ravens problem. This one's kind of a fun logic puzzle. If you don't get an intuitive feel for it, that's okay. Just make sure you understand what follows from it. So take the statement, all ravens are black. This is another generalization that you could put forward as a hypothesis. And like my other examples, you could then deduce a prediction from it and test it. And this works out to be such that if you find black ravens, they are evidence for the hypothesis that all swans are white. If you assume what these people who are trying to make an inductive logic said. So let's think about the claim that all swans are white, or sorry, all ravens are black. I'm sorry, I have messy drawing and messy writing. So you can carve up the world into 4 things. So there are the ravens, the non-ravens, the black things, and the not black things. So everything in the world falls in these 4 buckets. So there's the black ravens, the black non-ravens, the non-black ravens, and the non-black non-ravens. Obviously not to scale, but logically you can group all things in that way. So our statement is, all ravens are black. And people who are trying to develop an inductive logic wanted it to be the case that finding more instances of black ravens increases the probability that this statement is true. But unfortunately, here's a consequence of that. Or actually, first, so here's how you would represent this sentence here. All you're saying is that there's nothing in here. X meaning there's nothing in there. There are no non-black ravens. You're not necessarily, so let's say like X means there's nothing in there, and check means there is something in there. You're not necessarily committed to the claim that there are any black ravens. So take the sentence, all dinosaurs are reptiles. That's true, but there are no dinosaurs, at least not black. So when you say all ravens are black, all you're saying is there's nothing in this box. But what the logicians pointed out is finding things in here is as much of a confirmation for this as finding things in here is. If you assume that finding black ravens is evidence, inductive evidence, that all ravens are black, it is logically equally the case that finding non-black non-ravens is also evidence that all ravens are black. If that seems strange, again, I won't expect you to have an intuitive sense of that, but just you'll have to take my word for it. It is logically the case, and the book has a discussion of this, that finding things in here is as much evidence for this as this is, which seems pretty strange. So if you accept that inductive inference works, you have to accept that this blue water bottle, so not black, not raven, is evidence for this, just as much as seeing a black raven is. There's one other example of a consequence of trying to find inductive logic, but we're not going to worry about that. The takeaway from chapter 3 is that attempts to create an inductive logic were, as I say, a profound failure. This is where Popper comes in. Oh, sorry. I realized there was one video I forgot to show. So this is not as good at timing as it could have been, but I have a video of Peter Millikan, who's probably the world's authority on Hume, summarizing Hume's problem of induction. I mean, in a sense, all these other things are just footnotes to Hume anyways. So we'll watch that to close off chapter 3, and then we'll dig into the chapter specifically on Karl Popper. So get the lights. Okay, so it is these paradoxes and problems related to induction that motivated Popper to put forward his account of how we come to know things and how science works. The chapter starts with a brief discussion of Popper's history, his personal history. I'll add a little bit just for fun. Popper grew up in Austria. He started off as a Marxist. As a teenager, he was very intellectually curious and was a committed Marxist. He later became a social democrat of sorts. How many of you know the name Alfred Adler? I assume intro psych. He's the superiority-inferiority complex guy. So Popper interned for him. He worked for him. One thing that he noticed about both Adler and Marx is they seemed, or Marxists I should say, is he found that they could explain anything that seemed to go against their theory. So Marx put forward various predictions about what would happen. One is that the conditions of the proletariat, the working class, should get worse and worse over time. Whereas in fact, until maybe the 60s, but certainly in Popper's lifetime, in many ways conditions for them were actually getting better. But Marxists would say, well, that's because now the working class is in other countries. We've outsourced production elsewhere, so it's actually not evidence against the theory. And Alfred Adler would do the same thing. No matter what the kid did, Adler would say, he's striving for superiority. That's what's motivating all of his behavior. I'm sure many of you are familiar with Freudians doing the same kind of thing. No matter what the kid does, it shows that he hates his father, that kind of thing. And Popper thought this was really problematic. If any piece of evidence can be construed as supporting the theory in question, that's a big problem. Whereas he was very impressed with progress that happened in the physical sciences. So he was very familiar with the physical sciences, and he saw that they seemed to be doing something different. And he claims to have had his aha moment when he saw a newspaper headline saying, Newton refuted. So I don't know if any of you know the story. So according to Einstein's theory, it has several consequences, but one consequence of Einstein's theory that makes it different from Newton is that gravity can curve space-time and therefore can cause light to bend around. So a massive object can cause light to bend, and Newton's theory does not have this consequence. And what Einstein recommended as a means of testing this was to look at stars near the sun during an eclipse. Normally you can't look at stars near the sun because it's too bright, but during an eclipse you can see the stars. And the prediction is that the light from the star should appear to be somewhere where it shouldn't be. So normally when you look there it should be here, but when the sun's there, the light should appear here. That's a consequence of Einstein's theory, whereas it's not a consequence of Newton's. So they do the test, 1919, and Newton's predictions are falsified and Einstein's predictions are corroborated. Hence the newspaper headline, Newton refuted. And so Popper thought that's what makes the difference. What makes the difference between science and non-science is falsifiability. So a theory which is falsifiable is one that is capable of being proven wrong. So both Newton and Einstein's theory are falsifiable. So for Einstein, if the light had been here rather than here, Popper says that would have refuted Einstein. And given that it's able to stick its neck out like that and make a risky prediction that is capable of being falsified, that's what makes it scientific. Whereas Freud, Adler, and Marx, whenever they stick their neck out and make a prediction, if the prediction is falsified, they say, well, the theory's still true, we'll just kind of modify it to fit the new data we have. And Popper says that makes it thereby unscientific. So he published these ideas in The Logic of Scientific Discovery in 1934. As an aside, soon after that he had to flee Europe. Popper was Jewish and lived in Austria. He actually fled to New Zealand, where he wrote a book on politics, which he called his war effort. He couldn't fight the Nazis with weapons, so he wrote a book criticizing totalitarianism. That was his war effort. But he went on to develop the ideas in more detail. One important thing that Meehl said in that video earlier that I want to repeat, you will sometimes see it said that Popper was a positivist, and that's not true. Popper was not a positivist. He was in touch with the people in the circle, in the Vienna Circle, but he was not a positivist. Additionally, it is sometimes said that the falsifiability criterion was similar to the verifiability criterion. So the positivists, as we saw last time, had the idea that the meaning of a sentence is the method of its verification, and that any sentence which is incapable of being verified is meaningless, unless it's an analytic statement. And some people think, oh, so Popper is putting forward a falsifiability criterion of meaning. Any statement that is not falsifiable is meaningless. But Popper never said that. This is not a criterion of meaning. It's a criterion of what counts as science. So if something is unfalsifiable, Popper is very clear that it's still perfectly fine to research it or use it in other ways. You just can't say that it's science. So Popper's view was that metaphysics, metaphysical ideas, you're allowed to postulate them. What they are is they're like a holding ground for ideas before they are ready to be sciences. So when an idea is young and not fully developed, it's metaphysical. So think of like the early Greek philosophers, right, who had, for example, they developed the idea of atoms. They couldn't test it empirically, they couldn't do science on the idea of atoms. They were essentially just metaphysicians, just coming up with these ideas. It wasn't until later the idea was well developed enough to be a science. So Popper, unlike the positivists, was not against metaphysics, he just thought it wasn't science. Okay, one little funny video is from the show House. This is just a fun example of someone using unfalsifiable ideas. Do any of you know the show House, House MD? Yeah, right, so go ahead and get the lights. Funny little example of this. How does this help us with the problem of induction? So what Popper says is we should forget about induction. We don't need induction, it leads to all these problems. Let's just use deduction. We can treat theory testing not as a means of showing that a theory is more likely or probable or anything like that. Theory testing is purely a way of trying to disprove the wrong theories. And we should not pretend that it can do anything more than that. And to accomplish this, he uses a simple syllogistic argument called modus tollens. This is a good term to know. So here's modus tollens. And you can put anything here. It doesn't have to be H and O, but I'll use H and O just to keep it consistent. You could say A and B, it doesn't matter. But if H, then O, not O, conclusion not H. So this is deductively valid, this form of argument. So take my silly example from earlier. Let's say my hypothesis is that I am the strongest man in the world. And the observation is, that you'd expect is I can lift a felt. So that follows, right? If I'm the strongest man in the world, I can definitely lift a felt. Let's say I try and can't do it, so I cannot lift a felt. Therefore, I am not the strongest man in the world. Deductively, without any weird new inductive logic, that follows. So this is what Popper thought we should do. We should make up guesses, and when you make up H, that is for Popper an act of creativity. That's where the new ideas come from. You have to just kind of make them up. They can be informed guesses, but at bottom they are just guesses. Once you've made up the guess, then you have to be strict and rational. You have to deduce what would follow from that guess. So if the hypothesis is right, then I should observe this. I go look to see if I'll see it. If I don't, then I have falsified the guess, the hypothesis. So as I say, this involves some creativity because you have to make up the guess. But for Popper, they always stay guesses. All you can say is, it's a guess that has survived my attempts to prove it wrong. This makes Popper a fallibilist. There are other fallibilists in the history of philosophy. Fallibilist meaning you can't know anything with certainty. All knowledge is conjectural and therefore fallible. Relatedly, Popper is an anti-foundationalist. Foundationalism is an idea that I've talked about without using the term. So an example of a foundationalist is Descartes. A foundationalist is someone who thinks that the way to learn about the world is to find some foundations, some things that you can know with certainty, and that you can build the rest of knowledge on. So what's Descartes' foundation? What's the thing he thought he could know with certainty from last class? I think, therefore I am. So that's what you can know for sure, that's the foundation, and then he thought he could infer from that God existed, and from there that God would make sure his senses were reliable, and so on, and then you can build the rest of knowledge on that. Popper thinks that doesn't work. All knowledge is conjectural. You can assume some things, like take some things for granted. I'll use another term later, but there are things that Popper thinks are okay to take as kind of provisional foundations, but they are not known with certainty because all knowledge is conjectural. Okay, to reinforce this, I'm going to show another video. This one is of the physicist David Deutsch, who is a committed Popperian, a full-blown Karl Popper person. Have any of you heard of quantum computers? So David Deutsch is basically the person who invented them. So if he has something to say about how science works, it's worth listening. So he'll explain his account of how science got started, and it is thoroughly Popperian. So get the lights. Okay, so very well said by David Deutsch, and this goes against maybe an intuitive idea of how science works, that it's essentially just systematic observation. But in fact, it always starts with a guess. As Deutsch said at the end, Popper argued that all observation is theory laden. You can't observe without theory guiding what you see. I'll return to that point later in the chapter. But this is actually a great place for a break. So I'm ahead of where I thought I'd be, so we'll take a little bit of a longer break. Come back at 1, you can go stretch your legs, get coffee, and we'll pick it up from there. All right, let's get started again. So I don't see anyone following in the book, but I'm up to page 83 now. So what's implied by what I've already said is that Popper saw science as essentially a 2-step process. Step 1 involves creativity, where you put forward the conjecture, and step 2 is attempted refutation. One thing that he thought was very important to avoid, at least in most cases, is engaging in ad hoc modifications of the theory. So when there is an apparent falsification, changing the theory or doing other types of modification in order to avoid what looks like a falsification. Because it's always possible to do this. You can always change your theory to accommodate the new apparent falsification. I gave examples earlier of Marxists and Freudians doing that, and Popper thought that was very intellectually sinful, that you ought not to do that. However, he did have to acknowledge some exceptions to this principle. This is going to come up again when we talk about Lakatosh. There are several examples in the history of science where a theory looked like it was falsified, but there was so much going for it before, like it had done so well, and scientists did try to modify the theory or accommodate the falsification, and that modification actually turned out to be right. So the classic example is Newtonian theory for hundreds of years was doing well, but it could not explain the orbit of Uranus. I heard Neil deGrasse Tyson say it's Uranus, but I checked with Google, it is the funnier pronunciation. So the orbit was off. It was not what Newton's theory said it should be. Now, if you're a strict Popperian, that means you should throw out Newton's theory. Newton's theory makes a prediction about the pattern that the orbit should take. It does not have that pattern, so it's falsified. Throw away Newton's theory. But scientists did not do that, in part because there was really no alternative around at the time. So what they said was, there must be something else going on. What they posited was, there must be another planet that we haven't found yet that's tugging at Uranus and messing up the orbit. And they did some math and calculated that if that was true, it would have to be here, point the telescope in that direction, and voila, there was Neptune. So, in a certain sense there, that they were trying to protect the theory from falsification, which a sort of naive reading of Popper would say is bad, but in this case it worked out. So what Popper says is, okay, fine, it's sometimes okay to engage in these ad hoc modifications, but those modifications have to lead to falsifiable predictions themselves. So if you modify the theory to protect it against falsification, your additions or modifications themselves have to lead to new predictions. So in this case, they postulate, well, there must be another planet, which clearly does lead to a testable prediction. So in that case, it's okay. But generally speaking, Popper did not like these. The importance of these kinds of moves is going to be more emphasized by people like Kuhn and Lakatosh. Popper kind of reluctantly admits, yeah, we have to do them. People like Lakatosh and Kuhn will emphasize them more. The book discusses Popper's vision of what the ideal scientist should be, and it's implicit in what I've already said. A scientist should have two abilities. They should be creative They should be able to invent new ideas and strictly rational. So in the conjecturing part, that requires creativity, but the attempted refutation involves strict rationality. Now, Popper, again here more reluctantly, has to admit that often scientists are not like this. This is his ideal, right? Scientists should be constantly trying to disprove their theories. Most of you are probably far enough along now to know that's not often true. Scientists are human beings with confirmation bias like everyone else. Like, how many of you know the term p-hacking? How many of you have been exposed to this? So that's an example of hopefully a declining practice, but a very tempting practice wherein scientists will redo statistical tests in various ways until they get the result they want. This is unfortunately common. So one move that Popper makes, and others have developed more, is the idea that it doesn't have to necessarily be the individual scientist who's trying to disprove his own theory, but the community of scientists. Everyone has a kind of incentive to disprove the other theories, and therefore it's the community that engages in this conjecture and refutation. Popper also made an interesting analogy between his theory, actually, I don't know if I need to write this, but between his theory and Darwinian evolution. Many others have developed this as well, so in his view, you put forward these conjectures and then try to prove them wrong. And you keep the ones that survive your attempts to prove them wrong. And he thought that something similar happened with evolution, where you have random mutations that are put forward, and those which are not suited to their environment get selected against. And if a mutation survives and gets passed on, it doesn't prove that it's the best or the ideal one. It's just survived so far. It's just it's made it through the environment so far, but it might die out tomorrow. He also thought that this kind of process of conjecture and refutation should be applied in politics. As I say, he wrote a book on politics called The Open Society, and argued that politics should be about putting forward proposals and trying to test them, trying to show which ones don't work, and that we should not be, just as in science, we should not try to prove the one final true theory via induction or some other means. He thought we should not be too utopian. He thought that utopian ideals tend to lead to totalitarianism, and that change should be piecemeal. Okay, so that's an outline of Popper's thought. We're now going to move on to some problems with it. Ironically, even though Popper, in his writing, emphasizes the importance of open-mindedness and trying to prove your ideas wrong, I've heard from many people who knew people who knew people who knew him, and just reports of people who knew him, that he was not like this in his personal life. He ironically was very dogmatic, and if you criticized him, he was very angry. So kind of ironic, but I think it would not be in keeping with what he wrote if we were dogmatic about his views. I think we should subject them to criticism, and there have been a number of them. Some of them we'll be seeing next class when we talk about Kuhn. But the first problem I want to talk about relates to something we saw last class from Quine, which is that it's impossible to test ideas in isolation. This criticism applies to Popper as well. So remember that last time I said that if you want to derive a prediction from a hypothesis, you can't do so with the hypothesis alone. So it's not really if H then O. It's really if H1 in brackets and H2 and H3, etc., then O. You have to assume a bunch of things in the background in order to make the prediction. And so if we find not O, so it's been falsified, well, we haven't falsified H1. In logic, this means not, but what we've really shown is either not H1 or not H2 or not H3, etc. We've shown that something in here is false. Which one? As a matter of deduction, you can't know. This is what allows for ad hoc modifications. So in the case of the Neptune case, it's not the case that Newtonian theory alone implies that the orbit should be a certain pattern. It only does in conjunction with a number of other assumptions, one of which being there are no other objects nearby messing up its orbit. And it turns out that actually was the right thing to reject. So that's one problem with at least a simple kind of Popperian philosophy of science. And Popper actually acknowledges this, but a deeper problem is that many theories cannot deductively imply observational predictions about what you should observe. Many theories in science are probabilistic. Even though Popper wants to say, no, there's no such process as induction can't be justified, probabilistic inference can't be justified. Many sciences are just intrinsically probabilistic. Like quantum mechanics is probabilistic, the evidence for evolution is probabilistic. Many of Popper's examples come from physics, where arguably you can deductively deduce a prediction from a hypothesis, but in many of the other sciences that is just not possible. And Popper, at least in some of his writings, did try to say, well, I guess that implies that Darwinian evolution or these other things are just not science, they are metaphysical research programs. But that seems pretty absurd, and no one really took that seriously, and as I say, that's a pretty serious problem. Even though Popper wants it to all be deduction, many have argued that's simply not possible. Later in the course, we will see an attempt to deal with this, which is Bayes' theorem. That's an attempt to formalize probabilistic inference that worked better than some of the attempts we saw in chapter 3. Another problem with Popper is the idea of what do we think about a theory that has survived many experimental tests? So we have this guess, we subject it to experimental tests, and it passes them. What Popper wants to say is that just means they're not falsified. But that seems kind of weak. Presumably you want to say something more about whatever Einstein's theory or evolution or whatever your favorite theory is, more than just they haven't been falsified yet. Popper tried to answer this by inventing, well, he didn't invent the term, but he gave it a technical meaning. He said that what you can say is that a theory has been corroborated, or the term is corroboration. And what corroboration means is it has survived many risky tests. So if a theory survives many risky tests, the term that Popper uses is corroboration. A theory has been corroborated. So what does it mean to say that it has made a risky prediction, or it has survived a risky test? Here's a simple example. I'm stealing this from Paul Meehl. Suppose I make a theory of the weather, and this will be relevant at the end of class. At the end of class, I'm going to talk about some ways in which this connects with psychology, so this is a good example to think about. Suppose I make a theory about the weather, and it leads to the prediction that it will snow at least once in January in Edmonton. That's the prediction. And sure enough, it passes the test. So you're all looking kind of skeptical. That's not a very risky test, right? It's not very impressive if it passes the test because it's not very specific. If by contrast, my prediction was it will snow on these specific days and this specific amount, and let's say I predicted like 2 months in advance, no matter how goofy my theory is, you'll be more impressed that it has survived that attempted falsification. So you would say it was more strongly corroborated. Now, however, people still object because Popper still, if you push him, he will never say, therefore the theory is more likely or more probable, because that requires induction, and he doesn't want to touch that with a 10-foot pole. One similar idea that comes from someone who does accept induction, this is in the book, is, so for Popper, he would put it in terms of a risky test. But another philosopher of science who is fine with induction puts it in terms of a damn strange coincidence. This is a nice term. And what this means is the prediction should be such that it would be a damn strange coincidence if the prediction came true without the theory being true, or at least approximately true. So in my snow case, it would be a damn strange coincidence if my theory is completely false, but I was still able to predict the exact days and times that it snowed. And therefore it's more impressive. Whereas it's not at all a damn strange coincidence if my theory is completely false, but I'm able to predict that it will snow at least one day in January. And this relates to another term that Popper put forward. So what I just said was the prediction should be such that it would be a damn strange coincidence if the theory were not true, or at least approximately true. And you may think, what does approximately true mean? This is another thing that Popper tried to formalize. So in a strict logical sense, theories are either true or false. So Newtonian theory, Newtonian gravity, is technically false because it leads to some predictions that have been falsified. But clearly it's a lot better than the theory that the moon is made of cheese. It does predict a wide range of experimental outcomes correctly. In fact, it's good enough to get a man on the moon. The mission to the moon required no Einsteinian gravity. Newton's theory is good enough. So it's a very good theory. So what do we want to say about a theory like that? And what Popper says is theories like that have higher verisimilitude. Vera relating to truth, so like verily, veridical, and similitude meaning similar to. So meaning similar to the truth or a better approximation to the truth. This is a very useful idea to have in your head. Most theories are false. Even most good theories are false. But what they can have is more or less verisimilitude. Or have more or less approximation to the truth. Now, attempts to formalize this have been largely unsuccessful. Popper tried to develop a notion of it where you count up the consequences and figure out what percentage of them are true. That, for boring technical reasons, didn't work. But as an ideal, it is a useful concept. Okay, any questions about what I've said so far? Okay. So before I move on to some notes that go beyond the book, including some things that may help you with the paper, I want to close with one final problem that I want you to keep in your head when you read Kuhn, because this is a nice way to think about what Thomas Kuhn argues. So in debates about evolution, people often say, well, what would falsify evolutionary theory? Is evolution falsifiable? And the example that's often given, somewhat flippantly, is if we found a pre-Cambrian rabbit. So the idea here is, if we found a fossil of a rabbit, I forget what time period the Precambrian is, but some long period of time ago, long before there should be mammals in the standard evolutionary models. If we found that, that would falsify evolution. That's one common argument that's made. But when you pause and think about that, and the book has a discussion of this, that probably is not how it would go down. So let's say tomorrow a scientist digs up a rabbit, carbon dates it, or I don't think carbon date doesn't go back that far, but uses some dating method and concludes that it was in the Precambrian. Would biologists then just go, well, we give up, Darwinian evolution is wrong, we will stop our research programs? And the answer is almost certainly not, right? What most scientists would immediately conclude is probably there was something wrong with the dating method, or the fossil was incorrectly identified, or something like that. They would not throw away evolutionary theory immediately. And as we'll see in the Thomas Kuhn chapter, that's actually normal. If a scientific paradigm has a lot going for it, things like this are treated as anomalies. You know, like, yeah, something's probably wrong with that, we'll look into it and see what's wrong. Again, as long as the paradigm already has a lot going for it. So there's a bit of a teaser for what we're going to see with Thomas Kuhn. Okay, so I'll make a few more philosophical points, and then I'll start talking about how Popper's views connect up with psychology. One thing I want to briefly deal with, some of you may be thinking this, you may wonder, is this view self-refuting in the way that positivism was? And Popper was aware of problems like that, and he was very clear that his overall picture of how knowledge is created is conjecture and criticism. So it's not the case that you should only believe something if it's experimentally testable. He thought that the way you form knowledge about the world is conjecture and criticism can include philosophical criticism. And in fact, experimental refutation or falsification is just a special case of this. It's a type of criticism where you use experimental evidence rather than logical arguments, but that avoids the problem of self-refutation that the positivists had. Another problem that sometimes people think about is the idea that all observation is theory-laden, like David Deutsch said. It's impossible to observe without some theory guiding what you look at and how you look at it. And you may wonder, well, where do the initial theories come, like when babies are born or something? And Popper's view is that what babies are born with is inborn expectations, which are in turn produced by evolution. So Popper is not a blank slatist. He thinks that the early kind of proto-theories we have are just the expectations that we were born with that are shaped by evolution. And then evolution itself is also a kind of trial and error process that is in fact analogous to conjecture and refutation, as we saw earlier. And then one final point, and this one actually is very useful if you go on into graduate school and try to do research. So I said earlier that Popper is an anti-foundationalist. And that's true if you mean foundationalism in Descartes' sense, where there are foundations that you can know with certainty. But a term that I like to use, it's my own term, it's not from the book, is Popper is a kind of provisional foundationalist, meaning it's okay to take certain ideas as assumptions that you take for granted, but they can be revised. You don't know them with certainty, you just assume them for the sake of carrying out your research program or what have you. Quine, as we saw, actually had a similar view. And this is very useful when you're going on into graduate school. In the book that I have posted on eClass, Conjectures and Refutations, there's a great chapter called Towards a Rational Theory of Tradition, where he gives some advice to young scientists. It's a great passage, I won't read all of it, but the gist of it is, if you start doing research, you have to take a kind of research program or set of assumptions for granted. He says you are very badly advised if you are told by your supervisor, observe. Just go observe, go measure. You have to embed yourself into a research tradition, learn what the assumptions are, learn what the problems are, and try to move it forward. By the way, that chapter, Towards a Rational Theory of Tradition, would be very promising if, for section 5 of the paper, you want to integrate Popper and Kuhn. So in section 5 of the paper, you can either defend one of the two, say like Popper is right or Kuhn is right, but you can also try to integrate them. And in that chapter, Popper is in kind of a Kuhnian mood. So it would be promising if that's the approach you wanted to take. Now, speaking of the paper, something I forgot to mention last time. Oh, you don't have to turn the light. This is just the syllabus. So for section 2 and 4, where you have to draw a connection between the thinker and psychology, there are different things you can do. And the in-class essay on Chalmers and Dennett will be the same. So one thing you could do is you could explain how psychology, or this isn't in the text, or it could be a specific psychological theory, like say Freud or something, is or is not done the way Popper or Kuhn says it should be done. Or you could make a normative argument saying that psychology or a given area in psychology should be more like this person says it should be. So you have a lot of leeway, but those are the general kinds of things you should have in that section. So I forgot to mention that on Wednesday. And so I'm going to give here kind of a sampling. You don't have to choose any of these. You can go off and choose your own connection, but I'm going to talk about some implications of Popper's views for how we do psychology. One important one is, unlike the positivists, Popper is okay with positing theoretical constructs. So positivism is related to behaviorism in psychology, where it's not permissible to postulate what's going on in people's minds. You only deal with directly observable behavior. But according to Popper, it's perfectly fine to posit unobservable entities as long as those entities lead to predictions about what you should observe. So think of the fusion example, right? You posit that there's fusion inside the sun, and that explains and leads to predictions about what you should observe. One area in which Popper's ideas are used kind of by both sides of a debate is evolutionary psychology. So, as I'm sure many of you know, evolutionary psychology is a very controversial area. We'll be returning to it when we talk about Lakatos, one of Popper's students. But people who criticize evolutionary psychology often do so because they say it's unfalsifiable. You can't directly test whether selection pressures led to this tendency or that, whereas defenders of outside say that you, in fact, can test predictions from outside. I won't get into that debate, but that's an example of a way in which Popper is relevant to psychology. Of course, I mentioned in passing Freud and Adler. Both of them were criticized actually directly by Popper for being unfalsifiable. That's another example. Another connection, and this one's in the key terms, between Popper and psychological research is null hypothesis significance testing. This is something that Popper would probably not be very happy with, at least in a certain respect. So, you may not have seen this term, but I believe Stats 151 is required for this. Whether you saw this term or not, you all have seen this. Null hypothesis significance testing. So anything that connects to trying to get a p-value of less than 0.05 is essentially null hypothesis significance testing. So the idea is you have a null hypothesis, which is typically the hypothesis that there is no effect. So the drug does not reduce depression. The correlation between two variables is 0, right? So it's the hypothesis that you want to reject. You want to conclude the null hypothesis is false. And the p-value, apologies for the statistics reminder, but the p-value is the probability that you would get the result you got if the null hypothesis is true. So, classic case, you have the drug condition and the placebo condition, and let's say the happiness score average is 7 out of 10 for the drug condition and 4 out of 10 for the placebo condition. It almost certainly would not be that big, but let's just suppose. In that case, you would have a very small p-value. So the null hypothesis in this case would be these two are equally effective. There will be no difference between the two groups. Or I should say, just the drug doesn't work. So the p-value in this case is, what's the probability that you would get this difference if the drug doesn't work? And you want it to be below this cutoff. You want it to be less than 0.05%, or less than 5% likely that you would get the result you got if there's no effect. In other words, if the null is true. That should be reviewed, but any questions about that idea? So how does this connect with Popper? Well, theories in psychology, often, all they predict is that the null hypothesis is false. So they're not predicting there will be this exact amount of an effect, just there will be some effect. So as an example, think of Elizabeth Loftus's idea, constructed memory. You can pick any theory in psychology. It's almost always like this. Or I guess the term of the overall theory is constructive memory. So Loftus's theory is that memory is not like a video camera, right? It's fallible and gets reconstructed with subsequent experience. So how did she test this? Well, from this theory, she derived the prediction that if you have two groups, so a specific example was there's two groups, both of whom see a car accident, like on a video, and one is asked how fast were the cars going when they hit each other, and the other is asked how fast were they going when they smashed into each other. This is a classic test of constructive memory theory. And you want to see how fast do they think? Let's say it's, I don't know, I forget what it is, let's say it's 55 miles an hour and 25 miles an hour. All that Loftus's theory predicts is that the difference here will be greater than 0. And that it will be, or I guess I should say, it'll be large enough that the p-value is less than 0.05. But how big will the difference be? It's not able to make a prediction that specific. So unfortunately, these predictions are closer to the bad snow example, where you're just predicting there will be snow at some point in January. Because strictly speaking, if you make your sample large enough, eventually you're almost guaranteed to have the p-value be less than 0.05. Because the p-value says nothing about how big the effect is. It's just how unlikely is it if the hypothesis is false. And as your stats instructors may have told you, if you make your sample large enough, the probability of getting a p-value below 0.05 goes up. So it's not all that risky to say, I predict I will be able to get an effect with a p-value of less than 0.05. So that would be something that Popper may not be as happy with. One reason for this is that theories in psychology are typically verbal and not mathematical. There's a great paper someone named Machado. I forget his first name, but he talks about how theories exist on a range, from those that are more weak and therefore often verbal to those that are stronger. And by strong, he means they are very well defined and therefore very open to refutation. Right? The more precise a theory is, the easier it is to refute it. So take Newton's theory, like the inverse square law, which says how fast objects will accelerate when they're dropped. It's very precise. Any deviation from that falsifies the theory. Whereas theories like constructive memory theory from Elizabeth Loftus, they're not put forward as a set of equations that you can derive precise predictions from. All it says is you can change memory through words or misinformation. How much, under what conditions, exactly how much in condition X, you can't derive predictions that are that specific from theories that are made in terms of these kind of verbal statements. So that's another thing Popper may probably would have objected to. Okay, any questions about what I've said about this? Okay, a few final things I want to say. So one thing that will come up later, actually in the philosophy of mind section, is this process that Popper put forward of conjecture and refutation is analogous to many things, one of which is Darwinian evolution. Another, which I'll talk about in the philosophy of mind section, is Skinnerian conditioning, so where there's random behavioral outputs, some of which are rewarded and therefore increase in frequency. I'll say more about that in the philosophy of mind section. Actually, that I have already said. So that is all I have to say. We're finished significantly earlier than I'd anticipated, but any questions about Mr. Popper? Or Dr. Popper, I should say. Okay. Sorry, yes?
Sir Popper?
That's true, he's also Sir Popper. Yes, he was knighted, as the book says. Okay, so on that note, we'll call it a day. I will see you all on Wednesday when we'll get started on Kuhn, so make sure you're ready for the quiz on that.